At this exact moment, every photon arriving from the outer boundary of the cosmos has been traveling across 46.5 billion light-years of expanding dark void, and an invisible countdown is ticking toward the terrifying second when space shuts its doors forever. When you gaze up at the midnight sky on a clear, dark night, you might assume you are peering into an endless, infinite ocean of stars stretching out forever without end. But modern astrophysics reveals a harrowing reality. Our entire visible universe is trapped inside a colossal cosmic bubble, bounded by a physical wall of ancient light beyond which no observer can ever see. This is the observable universe, a spherical realm spanning 93 billion light-years in diameter, enclosing hundreds of billions of galaxy clusters, trillions of stars, gargantuan supermassive black holes, and the fading echoes of primordial fire. Yet right now, at this very instant, the distant edge of this cosmic sphere is accelerating away from us faster than the speed of light, systematically erasing the rest of the universe from our view forever. What mind-bending physics lurks at this ultimate edge of space, and why is the expansion of the cosmos actively isolating our galaxy in an endless ocean of permanent dark silence? To understand the true terror of the cosmic edge, one must first confront the absolute speed limit of the cosmos, the speed of light. Because light travels at a finite velocity of approximately 299,792 kilometers per second in a vacuum, looking outward into deep space is literally looking backward through time. When astronomers point a telescope at the nearest large galaxy, Andromeda, they do not see Andromeda as it exists today. They see it as it was 2.5 million years ago, when early human ancestors were first walking the Earth. As we look deeper into the abyssal void, targeting galaxies billions of light-years away, we trace cosmic history backward through billions of years, past newborn stars, colliding galaxies, and ancient quasars. Eventually, if we look far enough, we hit an impenetrable wall of radiant thermal energy emitted long before the first star ever ignited. This ultimate visual barrier is the cosmic microwave background radiation, the absolute oldest light in existence. Emitted roughly 380,000 years after the Big Bang, when the young universe cooled enough for neutral hydrogen atoms to form, this relic radiation represents the moment the cosmos transformed from an opaque, glowing plasma into transparent space. Before this epoch, free electrons continually scattered photons, creating an impenetrable fog through which no light could travel. The cosmic microwave background radiation forms the literal boundary wall of our visual universe, a glowing curtain beyond which visible light cannot penetrate. Beyond this curtain lies the unobservable universe, a realm so breathtakingly vast that its true extent remains completely unknown to modern science. Yet, the physical boundary of our observable sphere is defined not merely by light travel time, but by a bizarre cosmic phenomenon known as the particle horizon. Because the universe has been expanding continuously for 13.8 billion years, the distant regions that emitted the cosmic microwave background are no longer 13.8 billion light-years away. As their light traveled toward Earth over billions of years, the space beneath those light waves stretched continuously. Today, those original matter sources sit at a current physical distance of 46.5 billion light-years from Earth in every direction. This creates a colossal observable sphere 93 billion light-years across. But this massive scale raises an unsettling paradox that challenges our fundamental understanding of physics. If nothing in the cosmos can travel faster than light, how can the radius of our observable universe be 46.5 billion light-years in a cosmos that is only 13.8 billion years old? The resolution to this cosmic riddle uncovers the most profound and mind-bending property of space-time itself. While no physical object or signal can move through space faster than the speed of light, space itself can stretch and expand at any velocity it chooses without violating the laws of physics. According to Albert Einstein's general theory of relativity, space is not an empty, rigid stage upon which events occur. Rather, it is a dynamic, flexible fabric that bends under gravity, warps near massive bodies, and stretches continuously across cosmic scales. When we observe light from a distant galaxy redshifting toward longer, redder wavelengths, it is not simply because the galaxy is flying through space like a rocket. Instead, the very fabric of space between Earth and that galaxy is expanding, stretching the light waves as they travel toward our telescopes. For decades, astrophysicists believed that the gravitational pull of all matter in the cosmos would gradually slow down this expansion over time. But in the late 1990s, two independent teams of astronomers measuring the brightness of distant Type 1a supernovae discovered something that shocked the scientific world. The expansion of the universe is not slowing down at all. It is accelerating at an ever-increasing rate. The invisible driving force behind this cosmic acceleration was named dark energy. a mysterious form of energy that accounts for roughly 68% of the total mass energy budget of the universe. Unlike matter, which clumps together under the pull of gravity, dark energy is uniformly distributed throughout the vacuum of space, exerting an anti-gravitational pressure that forces galaxies apart at ever higher speeds. As dark energy pushes space outward, it creates a terrifying regime of superluminal expansion governed by Hubble's law. Formulated by astronomer Edwin Hubble, this law dictates that the speed at which a distant galaxy appears to recede from Earth is directly proportional to its distance. A galaxy twice as far away recedes twice as fast. A galaxy 10 times as far recedes 10 times faster. As you look further into the cosmic void, the cumulative expansion of all the intervening space builds up exponentially. Eventually, at a specific threshold distance known as the Hubble length, the rate at which space expands between Earth and a distant region equals the speed of light itself. Beyond this boundary, space expands faster than light, carrying distant galaxies away from us at superluminal speeds. This superluminal expansion creates a permanent barrier known as the cosmological event horizon, the absolute boundary of causal contact in our universe. Imagine standing on the bank of a raging river and attempting to swim upstream toward a waterfall. If the river current flows faster than your maximum swimming speed, no matter how hard you stroke, you will be carried downstream, unable to reach the upstream shoreline. In precisely the same way, when a galaxy located beyond the cosmological event horizon emits a stream of photons toward Earth today, those photons move through space at the speed of light. But because the space in front of them is expanding faster than the speed of light, the photons actually recede from Earth over time. They are forever trapped on a cosmic treadmill, destined to race across expanding void without ever reaching our solar system. The existence of this cosmological event horizon leads directly to a terrifying scientific reality. Right now, at this very second, 97% of all galaxies within our observable universe have already slipped beyond our reach forever. Although we can still see their ancient light emitted billions of years ago, the present-day versions of those galaxies are already receding from us faster than light. If humanity were to construct a starship capable of traveling at 99.99% the speed of light and launch it today toward those distant worlds, we would never arrive. Those galaxies have permanently exited our causal sphere. They are forever beyond our reach, isolated in their own independent regions of space, drifting into eternal cosmic solitude. This accelerating isolation brings cosmologists face to face with one of the most profound paradoxes in theoretical physics, the horizon problem. When radio telescopes observe the cosmic microwave background radiation coming from opposite sides of the night sky, regions separated by 93 billion light-years, they record a temperature that is uniform to an astonishing accuracy of 1 part in 100,000. Everywhere we look in the cosmos, the background temperature sits at precisely 2.725 Kelvin above absolute zero. In standard thermodynamic physics, such precise thermal equilibrium can only occur if two regions were once in direct physical contact, exchanging heat and energy until their temperatures equalized. However, when astronomers calculate the maximum distance light could have traveled since the beginning of time, they uncover a striking impossibility. The two opposite edges of our observable sky are separated by 93 billion light-years. In a universe that is only 13.8 billion years old, light and heat could not possibly have traveled from one side of the sky to the other to equalize their temperatures. These two vast regions of space should be completely disconnected, possessing entirely different temperatures and cosmological properties. Yet, they look virtually identical. How could two opposite ends of the cosmos, which were seemingly never in causal contact, share the exact same temperature down to the 5th decimal place? To resolve this baffling contradiction, theoretical physicist Alan Guth proposed a revolutionary concept known as cosmic inflation. According to inflationary theory, during a fleeting fraction of a second after the Big Bang, between 10 to the minus 36 and 10 to the minus 32 seconds, the universe underwent a phase transition that triggered an extraordinary period of exponential hyperexpansion. In less than a trillionth of a microsecond, the fabric of space expanded by a factor of at least 10 to the 26, doubling in size over 80 times in rapid succession. Before this hyperexpansion occurred, the entire region of space that would become our observable universe was a tiny subatomic patch smaller than a proton, where matter and radiation had plenty of time to exchange heat and reach perfect thermal equilibrium. When cosmic inflation detonated, it stretched that microscopic thermalized patch of space to a macroscopic scale far larger than our entire present-day observable universe in a fraction of an instant. This violent hyperexpansion smoothed out all major curvature and temperature variations, explaining why our sky appears flat, uniform, and isotropic today. But inflation also carries a mind-bending implication. Our observable universe is merely a minuscule, localized bubble inside an exponentially larger, unobservable multiverse. Beyond the 93 billion light-year boundary of our sky lies an unimaginable continuum of space that may stretch infinitely, populated by countless other observable bubbles that we will never see, measure, or interact with. As dark energy continues to stretch the universe unimpeded, the long-term future of our cosmic neighborhood grows increasingly bleak and terrifying. Over the next tens of billions of years, the cosmological event horizon will continue to shrink in relative terms compared to the expanding distribution of matter. Galaxy after galaxy, cluster after cluster, will be dragged past the event horizon by the accelerating expansion of space. Their light will undergo extreme gravitational and cosmological redshifting, stretching from visible light into infrared, then into microwaves, and finally into extremely long radio waves of vanishingly low energy, before fading into absolute darkness. In approximately 2 trillion years, every single galaxy outside our local group will have vanished beyond the cosmological event horizon. By that far future epoch, our Milky Way galaxy will have long since collided and merged with the Andromeda galaxy, forming a single mega-elliptical galaxy often called Milkdromeda. The inhabitants of Milkdromeda living trillions of years from now will gaze out into the night sky with advanced telescopes, but they will behold nothing beyond their own island galaxy. The cosmic microwave background radiation will have redshifted into irrelevance, diluted by a factor of trillions until it becomes completely undetectable. All distant galaxies will have vanished into the expanding void. Future astronomers living in that distant epoch will conduct meticulous observations of the cosmos, but their data will lead them to a completely false conclusion about reality. Looking into an empty black void, they will find no evidence that the universe is expanding, no trace of the Big Bang, and no sign that other galaxies ever existed. They will conclude that their single island galaxy is the entirety of creation, static, eternal, and surrounded by endless nothingness. The true history of the universe, with its billions of galaxies and violent cosmic origin, will be permanently erased from the sky, lost to the relentless acceleration of dark energy. This sobering far future scenario reveals a profound truth about our place in cosmic history. We are living in a uniquely privileged cosmological epoch. We exist during a narrow, fleeting window of cosmic time where intelligent observers have evolved early enough to look back across billions of light years, observe the birth of stars, detect the primordial afterglow of creation, and calculate the true scale of our expanding cosmos. Had human intelligence emerged trillions of years later, the ultimate story of the universe would have been forever hidden from our sight, erased by the expanding horizon. The terrifying edge of space is not a physical barrier of solid stone, energy fields, or impenetrable walls. It is a profound testament to the temporal and spatial limits of our reality. It reminds us that our universe is dynamic, evolving, and continually changing, moving relentlessly toward a state of ultimate isolation and maximum entropy. Every second that ticks by on Earth, another distant star system slips past the cosmological event horizon, severing its last light connection with our world and taking its unwritten history into the permanent dark. As we stand on our tiny blue world, looking out into the vast 93 billion light-year arena of the observable universe, we are forced to confront both our cosmic insignificance and our incredible good fortune. We may be small, fragile beings clinging to a rock orbiting an ordinary star, but for this brief cosmic moment, we possess the power to peer into the abyss, understand the laws of space-time, and marvel at the breathtaking majesty of the cosmos before the dark horizon closes forever. What hidden secrets do you think lie beyond the edge of our observable universe? Share your thoughts in the comments below, and subscribe as we continue to explore the deepest mysteries of space.